The next talk is from Suchitra Basak. She's my colleague on the QTune project. She's from the University of Plymouth at ICCMR. And she's going to talk about composing with quantum AUX and the Basak-Miranda algorithm.
Great. Thank you so much, Paolo, for the wonderful introduction. And before I begin, I'd also like to thank Carl because his paper, Quantum Music, was recommended to me by Dr. Miranda, and it was also my gateway paper into the world of quantum computer music. So without wasting much time, I'd like to get started. Let's share my screen. And my screen is visible, right? Great.
Yes, it's visible.
Thank you. And the presentation is visible now?
Yes,
great.
Everything's all right.
Awesome. So like Paolo already mentioned, I'll be talking about composing music with random walks and the Basak-Miranda algorithm. What we'll be covering in today's talk is a small introduction about automatic music generation, randomness, and what quantum computer music is. And then I'd like to talk about two algorithms, the three-dimensional quantum walk and the Basak-Miranda algorithm. I'll first explain these algorithms in the presentation, and then we'll move on to two demos using Jupyter notebooks. So what is automatic music generation? It's pretty self-explanatory. It's generating music with minimum human intervention. And when I say music, I talk about any kind of musical content, and the kind of content that is generated that depends on the aesthetic preference or the style of the musician. But in this particular case, in the two algorithms that I'll be talking about, the musical output that we are going to see is a set of numbers. And these numbers can be used in any way. In my example, there'll be MIDI notes. MIDI notes are numbers which are unique to every key on the keyboard. And every MIDI note corresponds to the corresponding frequency of that note. However, you can also use the numbers that are generated as synthesizer parameters, or as Omar had showed in his tutorials, you can also use the same set of numbers to trigger different samples. So you can use those numbers however you like. In this case, I'll be using them as MIDI notes. When we talk about generating music, a very simple way of generating music is by generating random numbers. And composers have always been fascinated by randomness because it gives you a chance to make your compositions more dynamic, more unpredictable. And why computers have been really good candidates when it comes to generating music with randomness is because of two reasons. They can be used to generate random numbers, and you can also give them instructions and add constraints according to your style or your preferences, and you can test the generated numbers. So you can generate randomness, and at the same time, you can also control randomness. And that's the reason randomness has been used very widely with computer music. And we'll be using quantum systems because quantum systems are inherently random. So it makes sense to use probability-based algorithms on quantum systems. So when we talk about quantum computer music, it means using either quantum hardware or principles of quantum physics for music generation. However, quantum computer music is like an umbrella term, and you can also use, talk about algorithms which are quantum inspired, or algorithms which use data generated by quantum computers to create music. So all these different algorithms are under, they fall under quantum computer music. And the aim of QTune is to create a set of tools that can be used by composers who want to experiment with quantum computer music. So what tools am I using? I'm using Qiskit and Max, and Omar already introduced these two tools in his tutorials. So Qiskit broadly takes part of the quantum part, and Max takes care of the sound or the audio part. Qiskit is used to design, implement, and test the quantum algorithm, test the musical algorithm, and you convert it into a quantum circuit. In today's demonstrations, I'll be using simulations. However, Qiskit can also be used to run your algorithms on a real device, on actual quantum hardware. And I'm using Max because Max is really useful software when it comes to prototyping and testing different audio algorithms. You can also use it with video, as Omar already showed us. And Max can be used to interface your algorithm with a bunch of different hardware devices and different DAWs, which are music creation softwares. Max is so powerful that you can even run art installations on Max alone. And how do I get Qiskit to talk to Max? This is done using a communication protocol called Open Sound Control, which is a common protocol. And I'm using a Python package called PyOSE in order to do that. So whatever circuit is implemented in Qiskit, the output is sent to Max via PyOSE. And you can also use the same protocol in Max and send data to Python. This is not the Max patch that I'll be using. This is just an example. All right, so let's move on to the first algorithm. And this is the three-dimensional random walk. Three-dimensional random walk, you can visualize it as walking along the edges of a cube, where each vertex of cube represents a musical outcome. So when you walk from one vertex to another, you're essentially selecting the next node. And when you walk when you're at one vertex, you have three other vertices that you can walk to, or you can decide to stay at the same spot. This means that there are four possible outcomes. Let me show you an illustration that would explain this better. So let's assume that I'm at this vertex, 0, 0, 0. I have four options. I can either go to 0, 0, 1, 1, 0, 0, or 0, 1, 0, or I can stay at 0, 0, 0. If I decide to move here to 1, 0, 0, again, I have three options. I can either walk here, I can walk along this edge, or I can walk along this edge, or I can decide to stay at the same vertex. So there are three important things to notice here. One, there are 8 vertices, so there are 8 possible nodes. Then there are 4 ways to get from one node to the next node, either these 3, or you can decide to stay at the same. And the third one is whenever you jump from one vertex to another, there's only a 1-bit change. So if you notice, take any 2 vertices, the difference between these two, for example, 1, 1, 1, 0, 1, 1 is 1 bit. So there's only 1 bit that is flipped when you walk from one vertex to another. And these 3 constraints are used to design the circuit. So there are these 3 input qubits, which are the 8 vertices, which are the 8 possible nodes that we can have. And these are 2 dice qubits. these two dice qubits correspond to the 4 different paths that you can take to go from one node to another. These dice qubits decide which bit is to be flipped. And now that we have the circuit, let's move on to the demo. So the 3-dimensional musical quantum walk, import the necessary libraries, which is always the first step, since you're working with Python. This is what the circuit looks like in Qiskit. This is the same circuit that we just took a look at in the presentation. Then I decided to create a function in order to use the circuit later. It just makes it easier. A function to execute the circuit with only one shot. So we only run the circuit once. And the next step is to generate a stream of notes. So we run the circuit multiple times, and we create a list of notes. Now, the next note depends on the previous note. So in order to do that, there's an option to set input. We need to set the input. Whatever the previous note is set as the input to the circuit. And then the circuit is run, and then running the circuit is equivalent to walking along the edge of the cube that we previously spoke about. Now sending data to max. Now there are 2 kinds of values that I'll be sending to max, pitch and rhythm. Pitch corresponds to the frequency of that note, how high or how low that note should be. And rhythm corresponds to the length of the note or the duration of that note. So the same circuit is executed twice. Once it's for generating the pitch, this half, and this half is for generating the rhythm. Now let's take a look at the different values of pitch and rhythm that we have received. If you notice that there's always a 1-bit change from 000 to 001 and then 101. This means that you're moving from one vertex to another. And now how do we sonify these values? How do we make music out of these numbers? So one way of doing that is by using a technique called mapping. So every possible state, every possible vertex that I have is mapped, or it's linked to a note on the Persian scale. Of course, you can use anything, any kind of scale that you like, but in this case, we've selected Persian scale. And we also have, in the case of rhythm, we have a list of rhythm options that this list is mapped to. So now that we have a list of pitches and rhythm that we like, let's send this data to max MSP. And how this data is sent. First, Python sends a note to max. Max plays that note. It's pretty simple. However, because the length of every note is different, whenever the note is done playing, max will send a value of a trigger to let Python know that it can play the next note. And once this message is received, Python sends the next note. So this is what the output sounds like. So that was a 3-dimensional quantum walk. Now we move on to the next algorithm. And this is the Basak-Miranda algorithm. There are the most interesting thing about this algorithm is that it uses Markov chains. Markov chains are used to create a stream of nodes. They are a probability-based algorithm, and every node depends on the previous node. So it's similar to how music is actually played in real life. Markov chains also make it easy to represent sequencing rules. Like in the previous example that we saw, there are only 4 possible states that one state can lead to. However, when we talk about Markov chains, we can make more changes. We have more flexibility when it comes to the kind of rules that we want, and we can represent them in a very simple 2-dimensional matrix that we'll be going through in the next slide. And we use the properties, the quantum properties of constructive and destructive interference. So this is what a Markov chain looks like. This is the 2-dimensional matrix that I was talking about. Now let's see how to read this matrix. So let's assume that the first node that we've set, the first, our algorithm is initialized to node E. What this row says is that the next node could be F or D sharp with equal probabilities. Now let's assume that the computer has selected F as the next node. Then we move on to the corresponding row, this one, and now we have 4 options. The next node could be E, G, D, or C with equal probabilities. So this is the same thing. So if the first node selected is E, I have 2 options here. Computer picks 1 out of the 2 options, and now I have 4 options if I select F. And this is how a stream of nodes is created. Every time a new node is selected, the computer goes back to the corresponding row and picks 1 node according to whatever rule this is. So how do we get the computer to do that? What are the steps? So the first step is to binarize the target states. So let's assume that the first node selected is E. Here F and D are the target states or the winner states. The computer is supposed to pick one of the 2, F or D sharp. So the first step is to binarize them. So F and D sharp are 1 and all the other values are set to 0. Then we create the oracle matrix. Now that we know that our 2 target states are the first and the 5th element in this list, these target states are marked. And this is the unitary of the oracle circuit that is created. Now let me take a pause and explain what this is. When I say the target states are marked, what I mean is that they are multiplied by -1. That is, the amplitude is inverted. And what is this? What does this represent? This is an identity matrix with 2 target states that are marked. In quantum computing, every element or every gate that we have can be represented as a unitary matrix. And this is the unitary matrix of the oracle circuit. This part, this matrix tells the computer that I would like to select 1 out of these 2 elements. And in order to make this more scalable, like, of course, we can always draw, we can always have a circuit that creates this unitary at the output. However, since Qiskit has this function and Qiskit is versatile, I decided to condense this unitary matrix into a gate. This makes the application more scalable. So you can use the same technique for all of the rules in that unitary matrix. And then the next step is amplitude remixing. It's again a unitary linear transformation, and this refers to inversion around the mean. The next slide will make it clear. So imagine there are two qubits in balanced superposition. The amplitudes of all the qubits are the same. So the probability of measuring one of these states at the output is equal. Then the oracle inverts the amplitude of the target state. So if I want Ket01 to be my winning state, then I flip it, I multiply it by -1, like what we did in the oracle matrix. What happens now is the average amplitude of all the four state falls. And the next thing is we flip around the new average amplitude. And because of that, the one that's already flipped, the winning state, the amplitude of this state increases. And that's how the circuit knows that I need to select the one with the highest amplitude. Now, putting all these elements together, we first apply Hadamard gates to put all the qubits in equal superposition, and which is again a very standard step in many quantum algorithms. Then we apply the oracle matrix, that is, we mark the winning states. Then we apply the amplitude remixer, which is when we flip the when we flip the amplitudes along the mean. And then we apply measurement gates, that is when we are moving from the quantum to the classical domain. And now that we have the circuit ready, let's take a look at the demo. So the step one is designing the circuit. This does mean putting data, making the circuit, like making the markout chain more legible. Again, let's assume that the first note is E. The first step was to binarize the target states. So we know that the first element and the fifth element are to be selected. So let's mark them as 1. Then we create the oracle matrix where we take a unitary matrix and mark these two states. The first and the fifth state, we multiply them by -1. And then we build the circuit. So initialize the circuit, apply Hadamard gates. We then design the oracle, which is taking this matrix and writing it as a single gate. And then we write the circuit which performs the amplitude remixing. Then we put it all together. This is what the final circuit looks like. When we execute this circuit, this is the output that we get. State number 1 and 5 have the highest probabilities. And that is what we'd expected, because these two are the winning states and we need to make a selection between these two. And then we calculate the next node. The node with the higher probability is selected. And then this data is sent to max. The same program is run multiple times. In this case, it's run 48 times. And all the nodes that are generated are sent to max. So let's listen to the output. Right. I'll quickly show you what this max patch looks like. I have used the same max patch for both the demos. Whatever data is received, it's directly sent. If it could either be a pitch value or it could be a pitch and a rhythm value, like we saw in the previous demo. And if it's a rhythm value, it's mapped here. It's mapped to one of these possible rhythm values. If you have more questions about how these values, or from where these values are and what these values mean, I'll be sending a link to the paper and you can check out, I think it was figure number 15, figure 11. And that has more details about this. And whatever values are received are, excuse me, are all sorry. And all the values that are received are condensed into one note.
Okay, that's it?
No, and
oh, sorry.
Just one last slide.
Sorry.
So this is the reference that I was talking about. This can be found at this link, and all the images that I have taken are from this paper. And that's it. It's the answer. Thank you so much.
Okay, sorry, Suchitra, for the intermission, but okay, thank you for your presentation. It was really great. We had a question a while ago in the Q&A section. I think Eduardo answered it, but I think it's nice to put this on the live recording, that a person was asking about the first half of the presentation about the quantum walks, and it was really questioning the difference between a classical quantum walk and a quantum, a classical random walk and a quantum random walk. What do you think the differences are, if there are any?
I think conceptually both are the same. The only difference is the way the algorithm is applied. So
okay,
in the case of a classical random walk, you'd use classical probability based algorithms, and in the case of a quantum walk, we can use, we can initialize qubits according to whatever probabilities we want, and we can use the inherent randomness that quantum systems possess.
Okay, thank you. We have another question from Hari. How do we design a quantum circuit from Markov chains? I'm aware that the circuits has to be armed in superposition at the beginning, but for the rest of the circuit, is there any specific rules? So I think maybe you can explain about.
So there are, like any other engineering problem, there are various ways to solve the same problem. One way of using Markov chains is by using the Basak-Miranda algorithm. Another way of using Markov chains could be, like I previously said, you can take a qubit and initialize it at a particular value. Or you can apply a rotational gate, an RY gate, and initialize it. So that would be another way of using Markov chains. And of course, in this case, I'm only talking about one-dimensional one. And there's also there are also other papers about quantum walks and Markov chains in the literature.
Okay, that's great. I really like that the Basak-Miranda algorithm has a very interesting way of connecting with Max and connecting with the idea of how things can be designed in a similar way that we can do with classical algorithmic composition. For example, you showed the cube example in the random walk, but really the Markov chain really generalizes this concept. And I think that quantum computing media really helps us with bringing this together.
Thank you so much, Paulo.